Hello everyone. In this video, we're going to take a look at an integration technique called trigonometric substitution. Now, it's very common to encounter integrals that involve terms like the square root of some number squared plus x squared, or the square root of a squared minus x squared, or the square root of x squared minus a squared. For example, something that looks like this. Now, we have no way currently of evaluating integrals that involve terms like this. Well, that's what trigonometric substitution is going to help solve. Now, it's also interesting to note that even if your integrals don't involve square roots of values like this, for example, if your integral just involves something like x squared plus a squared, you can still use trigonometric substitution if there are no easier techniques available, because after all, you can write a squared plus x squared as the square root of a squared plus x squared squared, right? Okay, so even though your integrals may not exactly involve terms like this, you can still use trigonometric substitution in certain cases. Now, there are going to be three cases that we consider with trigonometric substitution. And down here we have them listed. So first of all, if your integral involves the square root of a squared plus x squared, where a is a constant, then we're going to use a substitution like this: x equals a times the tangent of theta. Okay, so to get an idea of how this substitution works and why we want to use it, consider this diagram that we have right here. So here we have a triangle. Okay, angle right there is theta. So of course, from this diagram you see x over a equals the tangent of theta. So x equals a tangent theta. Okay, so that's the primary substitution that we're going to use. Now, differentiating this, we get dx equals a times secant squared theta d theta. We get that. So if our integral has this term in it and say other x's, like say it's x divided by this quantity, so we would substitute for x the a tangent theta, and then if we had a dx out here, the dx would become a times secant squared theta d theta. And then if we look at our diagram up here, we see that if I look at the hypotenuse over the adjacent side, okay, so that's going to be the secant of theta, right? So the square root of a squared plus x squared over a equals the secant of theta in this case, right? Secant is hypotenuse over adjacent, right? So we get the square root of a squared plus x squared equals a secant theta. Okay, so, in other words, with the first case here, if you had an integral that looked like this, x over, say, let's make something else, like say x squared over the square root of a squared plus x squared dx, your x squared would become a squared tangent squared theta. The square root would become a secant theta, and the dx would become a secant squared theta d theta. You do all of these substitutions, and then this would turn into an integral involving powers of secant and tangent, and then you can evaluate it. All right, so that is case one. That's integrals involving terms that have the square root of a squared plus x squared. Now let's take a look at case two. Now, if your integral involves the square root of a squared minus x squared, where a is a constant again, then notice how we have a triangle drawn a little differently over here. Okay? So now you notice that if we label the opposite side as x, the hypotenuse is a, then the adjacent side down here will be the square root of a squared minus x squared, right? And so what we get then is, considering this, we have that x over a is the sine of theta. So x is going to be a sine theta. Dx will then be a cosine theta d theta, right, when we differentiate this. And then the square root, notice looking at this diagram, the square root of a squared minus x squared over a, so that's adjacent over hypotenuse, that is going to be the cosine of theta. And so your square root will become a times cosine of theta. All right? And that, of course, will be for x between negative a and positive a. You see, what's underneath the square root here has to be positive. So that means if we set a squared minus x squared greater than or equal to 0, that means that x has to be between negative a and positive a. In which case, the theta is going to be between negative pi over 2 and positive pi over 2, right? You see, if x varies from negative a to positive a right here, then think of that triangle as varying from down here. It might look like this, you know, where x is close to negative a, right here, if that side is a, x is close to negative a, so this angle right here, theta, would be close to negative pi over 2. And then if x goes up towards a, varies close to a, here's x and here's a, then this angle right here will be close to positive pi over 2. So that's why we get these limits right here. Okay, so these are the substitutions that you would use when you encounter an integral that has this term in it. All right, now let's look at case 3, and then we'll look at some examples. Now in the third case, we're going to consider integrals that have the square root of x squared minus a squared involved in the integrand. Now in that case, we want to draw triangles that look like this right over here. So you see how we have this labeled. We label the hypotenuse as x, the adjacent side as a, so that in this case then, the opposite side is going to be the square root of x squared minus a squared, which is what we have right here. Now in this case then, you see the x over a, that's going to be our secant of theta. And so you see we get x equals a secant theta as our primary substitution. And then the dx, derivative of secant, is secant times tangent. So dx is going to be a secant theta, tangent theta, d theta. All right, so that's what the dx is going to become in your integral. Now, looking at this diagram, you'll notice that the square root of x squared minus a squared over a is the tangent of theta. So moving the a over to the other side, we get that the square root is a tangent theta. However, we have two cases actually down here. You'll notice that this x squared minus a squared must be bigger than or equal to 0, right? So that means that x has to be bigger than or equal to a, or x must be less than or equal to negative a. Okay? Now in this case here, we consider the triangle as being drawn just in the first quadrant right here. So this would be x, this would be a. So you see the x is positive, and so x over a is going to be positive. Remember, a is supposed to be a positive number. This is going to be theta right here. So x is equal to a secant theta. And everything is positive as it should be. Okay. So, and you'll notice that in this quadrant also, the tangent of theta is positive, and we want the a times the tangent theta to be a positive number, which it is. Okay, so in the first quadrant here, when x is bigger than a, we consider theta to be between 0 and pi over 2. Now, if x is less than negative a, then in order to get everything to work out, we have to draw the triangle in the second quadrant, in which case we get something that looks like this. So this would be x, this would be a, and our angle theta would be right here. Okay. So then in this case, you'll notice that x over a equals secant theta, so x equals a secant theta. Now you see we need the x to be a negative number, right, because x is supposed to be less than negative a. Well, if we put the diagram in the second quadrant, in the second quadrant here, the secant will be negative. This is less than 0 when theta is in the second quadrant, as we have it labeled here. Okay, so the x will be a negative number. If we write x as a secant theta, then x will be a negative number. However, we also need the square root to be a positive number. So if we label the square root as being a tangent theta, well, in this quadrant, the tangent of theta is also negative, but we want the positive square root here, so we have to put a negative out in front here. So that's how everything works out. So if x is supposed to be less than negative a, then in your integral you have to substitute negative a tangent theta for the square root of x squared minus a squared. So these are all the substitutions that you would use in case 3, when your integral involves something like the square root of x squared minus a squared. Now let's take a look at some examples, and they will help to clarify all of these cases. Now in our first example here, we want to evaluate the indefinite integral of x cubed divided by the square root of 9 plus x squared. So we have an integral involving the square root of 3 squared plus x squared. So we're in case 1 that we had just described. So what we want to do then is draw a triangle like this, you see, and we want to label the opposite side as x, the adjacent side as 3, so that way the hypotenuse becomes 9 plus x squared. So you see we have the hypotenuse matching up with what is in our integrand. So then our substitution here, you see x over 3 is tangent theta, so this is going to be our substitution. The dx is going to be 3 secant squared theta d theta, right, when we differentiate this. And the square root of 9 plus x squared is going to be 3 secant theta. And if you're unsure of that, once again, look at the diagram up here. Notice if I take the hypotenuse and I divide it by the adjacent side, okay, that will give me the secant of theta. And then just multiply the 3 over. So these are all of our substitutions here, right here. All right, now we just put everything in. X cubed that becomes, if I cube this, 3 cubed is 27. Tangent of theta, we cube it, right? Okay, so there's x cubed, 27 tangent cubed theta. The dx, that becomes 3 secant squared theta d theta. So right here is dx. Okay. And then the square root becomes 3 secant theta. And right here is the square root. Okay, so now you see we have everything written in terms of powers of secants and tangents. Simplify this and let's try to integrate it. Okay, now you notice here we have a secant squared over secant, so one of these secants cancels, the 3 cancels, and what we end up with is this right here. So you see we get 27, pull that outside, tangent cubed, and we have 1 secant left over. Now if you look back to the cases for powers of secants and tangents, you'll notice that here we are in case 2. So in this case, we want to pull 1 tangent away, put it with the d theta, 1 secant away, put it with the d theta, and then use the substitution u equals secant theta. And then du is going to be secant theta tangent theta d theta. Okay, so right here you see down here, we pulled away a secant tangent from our integrand. Okay, now the secant, we only have 1 secant, so it just sits there, right? But we moved 1 tangent from here over to the d theta, right? Now, you want to use the substitution u equals secant theta, but you have to change this tangent squared into secants. Well, remember our trig identity, tangent squared is secant squared theta minus 1, so right there it is. U is secant theta, so this becomes u squared minus 1. This becomes du, and here we go. Now this can be easily evaluated. It's just a polynomial in u, evaluate it, and we end up with this. Now just notice that when we integrate this, you get 27 times u cubed over 3 minus u plus c, and then distributing the 27, you obtain this down here. So 9u cubed minus 27u plus c. Now what you have to do is go back through your substitutions and get back to the x's, right? We did 2 substitutions to get to this point, so we have to go backwards with our substitutions to get back to the x's, okay? So first of all, our first substitution, the u here was secant theta. Okay, so we put secant theta back in place of all the u's, and we get this right here. Okay. Now, what was secant theta in terms of x's? Well, if you go back to your diagram, which I'll just quickly redraw right here, remember our diagram looked like this, and I always recommend drawing these diagrams. Okay, so this was our x. Right, and this was theta. So from this diagram, you see that the secant of theta is the square root of 9 plus x squared over 3. Or you can also see that from your substitution that we used right here. But I think it's a little easier to pick it off from the diagram. Okay, so always draw these diagrams when you're doing these problems. Now what you have to do is just substitute this in place of all the secants. Okay, so you notice we have a secant cubed here. If we cube this, that's going to give us 9 plus x squared to the 3/2 power over 27, right? And so we put that in place of the secant cubed right here. And so you'll notice that what we end up with is 9 plus x squared to the 3/2 over 3, right? When we multiply the 9 against the 27. We get 1/3, okay? So we end up with this term here. When we put the square root 9 plus x squared over 3 in place of the secant here, you end up with just 9 times the square root 9 plus x squared. Okay. Notice the 27 over 3 gives you the 9 here. And then plus c, and finally here is our answer. So that is the antiderivative right here of x cubed divided by the square root of 9 plus x squared. There you go. That's how we have to do that problem. Let's take a look at another example. Now here we have an example of a case 2 problem. So we want to evaluate the indefinite integral of x squared divided by the square root of 4 minus x squared. All right, so once again, we draw a triangle and we have to decide how do we want to label the triangle so that we get out a 4 minus x squared. Also notice the 4 is going to be 2 squared. So our a in this case is going to be 2. All right, so here's how we decide to label the triangle. We label the opposite side x, the hypotenuse 2, and then that way the adjacent side by the Pythagorean theorem is going to be the square root of 2 squared minus x squared, right? Just using the Pythagorean theorem. And so we get then that x over 2 equals the sine of theta, in which case we get this as our primary substitution. So x is going to be 2 sine theta. Dx is going to be 2 cosine theta d theta. And then if you look at this diagram up here, you'll notice that the square root of 4 minus x squared over 2, that's equal to the cosine of theta. Move the 2 over, and you get that the square root is 2 times cosine theta. All right, now with all of these substitutions, let's go back to our integral and start substituting. So here's our indefinite integral. And now when we do our substitutions, x is 2 sine theta, so x squared becomes 4 sine squared theta. The dx becomes 2 cosine theta d theta, so right there is the dx. The square root becomes 2 cosine theta, so right there it is. And now at this point we can simplify and evaluate this integral using the cases of powers of sines and cosines. Now you notice that here these two nicely cancel. Okay, so we end up with the integral of 4 sine squared theta d theta. All right. Now if you think back to the cases of powers of sines and cosines, this is a case 3 problem. So we have to use the substitution sine squared theta equals 1 minus cosine 2 theta over 2. So substitute this in place of sine squared theta. Right there we have it. And now you just have to break this integral up and evaluate it. First notice that 4 and 2 of course cancel to give us just a 2 out here. And then just distribute the 2 inside and you obtain this integral right here. So we need to evaluate the integral of 2 minus 2 cosine of 2 theta d theta. All right, now you'll notice that from here, let me just elaborate on something. The integral of 2 d theta is just 2 theta. Now the antiderivative of cosine 2 theta, that's going to be the sine of 2 theta times 1/2, right? Little integration by substitution there. Just notice that if we were to differentiate this, we would pick up an extra 2 that we don't want because of the chain rule. That 2 right there, we would pick up an extra 2, so we have to multiply by 1/2. Now this 2 and that 1/2 cancel, and we just end up with 2 theta minus sine of 2 theta plus c. Okay, and that's what we have right down here. And there you go. We now have our answer, but we want it in terms of x. So we have to go back through our substitutions and try to evaluate this in terms of x. Okay, so that's what we do down here. Okay, so we're sitting right here. Now what we need to do is go back through the substitutions here and go back to the x's, okay? Well, the theta right here, how can we figure out the theta? Well, you notice from this equation, x equals 2 sine theta. If I write that as x over 2 equals sine theta, then what we can do is this implies that theta is going to be the arc sine of x over 2. Okay, so there you go. That's theta in terms of x's. That's all we can do. So that is right here. Okay, 2 theta. Theta is the arc sine of x over 2. Now, as far as the sine of 2 theta goes, that's a little problematic. Well, we need to use a trig identity. The trig identity we need is that the sine of 2 theta is 2 sine theta cosine theta. Okay, that's a trig identity. I'm giving you that now. You'll see that every now and then. Okay, so we replace the sine 2 theta with sine theta times cosine theta, or 2 times sine theta times cosine theta. Now we can replace the sine theta. So from our diagram up here, or just looking at these equations, the sine theta is x over 2. So we put in place of this theta, sine theta right here, we put an x over 2. So right there it is. There's x over 2. Now for the cosine theta, if you think back to your diagram, I'll just quickly jot it down right here. Okay, right here was theta. The cosine of theta is adjacent over hypotenuse, so that is the square root 4 minus x squared over 2. Or you can pick that off from this substitution right here, right? And then we replace the cosine theta right here with the square root 4 minus x squared over 2. So right there it is placed in for the cosine of theta right here. And now we have our answer finally, with a little simplification of this line right here. Simplify this a little bit, like notice that those 2's right there cancel. And we get 2 arc cosine x over 2 minus 1/2. That 2 right there comes from this 2. X times the square root of 4 minus x squared plus c, and there is your answer. Okay, so there you have it. That is an example of case 2. Let's take a look at another example. Now here we have an example illustrating case 3. So we'd like to evaluate the definite integral from the square root of 3 to 2 of the square root of x squared minus 3 divided by x. Now down here we have a diagram illustrating the substitution that we want to use. So notice that the square root of x squared minus 3, you can write that, of course, as the square root of x squared minus, and then the square root of 3 squared. So in this case, our a is going to be the square root of 3. That's the a. And so we have to label our triangle diagram so that we have the square root of x squared minus 3 appearing somewhere in our triangle as one of the sides. So the way we do this is we label the hypotenuse as x, the adjacent side as the square root of 3, and then the opposite side will be the square root of x squared minus the square root of 3 squared, which is just 3. So then you see we have the square root coming out as one of the sides. And we choose the x to be the hypotenuse and root 3 to be the adjacent side, just a standard convention. You know, you could choose the square root of 3 to be the other side, and then the square root of x squared minus 3 would be the adjacent side, so you could flip these. But the procedure would basically be the same, but you know, instead of secants, you would have cosecants, and so we just choose to do it in this manner for consistency. So now you see that x over the square root of 3 is going to be the secant theta. Okay, so then multiplying root 3 over, you see that you get x equals square root of 3 secant theta, so that is going to be our primary substitution. Differentiating this, dx is going to be root 3 secant theta tangent theta d theta. All right, right there. And then the square root of x squared minus 3 is going to be root 3 tangent theta. And that comes from the fact that, you know, if we look at opposite over adjacent, that's the tangent of theta, right? Square root, that's the tangent of theta. All right. So, also notice that since we're evaluating a definite integral from root 3 to 2, so the x varies from the square root of 3 up to 2, so in other words, x is bigger than the a term, that means that we want to set the square root of x squared minus 3 to equal positive square root of 3 tangent theta. In other words, the theta is going to be in the first quadrant. If you think back to case 3, we had a choice here whether this should be positive or negative square root of 3, depending on whether x is bigger than a or less than negative a. Well, in this case, x is bigger than a, so we want to choose the positive square root of 3 tangent theta. Okay? Now, with these substitutions, we're first going to evaluate the definite integral, and then we'll put our limits in afterwards. So the square root, x squared minus 3, we substitute in root 3 tangent theta, so right there it is. The dx is root 3 secant theta tangent theta d theta, so right there is the dx term. And then the x in the denominator, that is root 3 secant theta, and right there it is. All right, now let's simplify this and evaluate it. So notice we have some cancellation here. All right. And so we end up with root 3, bring that outside. And we have the tangent squared theta then. So we end up with this. Now this is a case 3 problem. You want to convert the tangent squared into secant squared theta minus 1. So right here we have it simplified. Because now you can integrate each of these, right? The antiderivative of secant squared is tangent. Antiderivative of 1 is just theta. So right here we are. Okay, and then let's just put these back in terms of x, and then put in our limits of integration. So So we want to convert this back into x's. So remember from our diagram up here, the tangent of theta is this quantity right here. So just put that back in place for the tangent of theta. Now the theta, okay, we have to go back to this equation right here. Okay, so x over root 3 equals the secant of theta. So that means that theta equals the arcsecant of x over root 3, like that, which you could also write as the arc cosine of root 3 over x, if you'd like. Okay, I don't have that written like that over here, but that's what you could do. And then you see substituting this in for tangent, the root 3's will cancel, and you'll just get this. And then substituting in for theta, the arcsecant of x over root 3, we have our answer to the indefinite integral right here. Now if we want to evaluate the definite integral with the limits, well, we can just put root 3 in here for x and 2 in and subtract. So that's what we have right here. So if we put 2 in here for x there, and then over here, you'll find that what we get is this is going to be the square root of 4 minus 3, so that'll just be square root of 1 minus root 3, and the arcsecant of 2 over root 3, if I put the 2 in there for x, that's the same as the arc cosine of root 3 over 2, and that's going to be pi over 6. So this is going to become, when we put 2 in place for that x, this is going to become root 3 times pi over 6 right there. And then when we put the square root of 3 in here for these x's, this is going to become 0. And the arcsecant of root 3 over root 3, which is the arcsecant of 1, is the same as the arc cosine of 1, which is 0. Okay, so we just get 0, and you could check that out on your calculator if you'd like. And so this is our answer, 1 minus root 3 times pi over 6. And this is what it's approximately equal to. All right.